Welcome and thank you for joining this webinar, From Processor-Centric to Data-Centric Computing, Architecting the Future of Intelligent Computing, prepared by the Alpert Research Team. I want to pull this all together. Let's do a comparative trade-off analysis. Let's pit these architectures against each other objectively.
The best way to evaluate them is to return to the fundamental energy equation that governs all computing today. Total energy cost, let's call it C total, equals the energy cost of the computation, plus the energy cost of memory access, plus the energy cost of network transmission.
So C total equals C compute plus C memory plus C network. Let's grade the contenders. Start with GPUs.
GPUs score perfectly on performance and parallel throughput. They have an incredibly mature software ecosystem.
But they score terribly on C memory.
They rely on external high-bandwidth memory that draws hundreds of watt power. They are fast, but they are power-hungry monsters.
Next, TPUs.
TPUs are vastly superior for dense tensors. Because their systolic arrays keep the data circulating internally, they dramatically lower the C memory cost compared to GPUs. But they trade off flexibility. You cannot easily use a TPU for anything other than matrix math.
What about compute and memory, the analog crossbar arrays?
CIM offers the absolute lowest C total possible for matrix math. It practically drives both C memory and C network to zero because the computation happens physically inside the memory cell.
But it struggles with precision due to analog noise.
And the software ecosystem is incredibly difficult to build.
And finally, neuromorphic spiking chips.
Neuromorphic offers the highest potential energy efficiency in the world for sparse, event-driven temporal data. It mimics the brain, but it requires abandoning binary calculus entirely, and the software ecosystem is barely out of the womb.
So, objectively, there is no single winner. There is no silver bullet architecture that will replace von Neumann entirely.
The winning strategy for the future of computing is ultra-heterogeneity. The ultimate data center of the future will feature a host CPU acting as the conductor. When a dense AI training task arrives, it routes it to the TPU. When a low-precision edge query arrives, it routes it to the CIM array. When a sparse sensor feed arrives, it routes it to a neuromorphic chip.
We will dynamically route tasks to the specific underlying physics that suit them best. Strategic implications and industry outlook. If I am an executive, a developer, or just a tech enthusiast trying to understand where the world is going, what is the roadmap?
The most critical takeaway is that hardware is no longer the limiting factor of innovation. We have invented brilliant, world-changing hardware, CIM, neuromorphic, quantum.
So what's the holdup?
The new bottleneck is the software ecosystem. Programming this post-von Neumann hardware is lagging years, maybe a decade behind the silicon. The most important investments right now are in tool chains and advanced compilers like MLIR that can translate human ideas into analog voltages and quantum superpositions.
We're already seeing the financial reality of this play out. Billions in venture capital are flowing into AI hardware startups.
And look, the hyperscalers, Google, Meta, Microsoft, Amazon. They are no longer waiting for traditional silicon vendors to solve their bottleneck.
They are all designing their own custom in-house silicon,
Explicitly tailored to their own internal algorithm, because the energy cost of relying on standard von Neumann servers is simply unsustainable.
The era of the free lunch is definitively over. For decades, software engineers could write sloppy code and just wait 2 years for Moore's Law to deliver a processor that was twice as fast.
Future leaps in performance will not come from passively shrinking transistors. They will require algorithm hardware co-design. Software engineers must deeply understand the physical layout of the hardware, and hardware designers must intimately understand the specific mathematics of the algorithms. They must be forged together.
We have covered so much ground today. We've talked about stacking memory chips like skyscrapers. We've talked about pulsing voltages through microscopic resistors to simulate biological synapses.
The von Neumann architecture will remain foundational, but AI-scale workloads are exposing fundamental limits in memory movement, energy efficiency, and scalability. Future systems will increasingly combine heterogeneous accelerators, memory-centric computing, and post-von Neumann paradigms to create intelligent, distributed compute fabrics spanning the edge-to-cloud continuum. Organizations that fail to adapt risk falling behind in the next era of AI-driven computing. If you are interested in gaining a deeper understanding of the transformative power of wireless technology, join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.
Thank you so much for joining us on this deep dive into the physical and architectural future of our industry. Keep exploring, keep questioning the paradigms, and we will catch you on the next one.